that if we live in a universe of wound dimensions, how do we distinguish between illusion and reality?
If you think about the beginnings of modern physics, you can start with Galileo, you can start with Newton, but in any event, we're talking on the order of hundreds of years. And the amazing thing, in hundreds of years, we've gone from a complete lack of understanding about how anything in the world actually works to the development of Newton's equations, where you can make fantastically accurate predictions about solar eclipses or lunar eclipses or motions of the planets and so on. And then, a couple hundred years after that, we migrate from that understanding, which is basically an encapsulation of the patterns that we can all discern with the naked eye. We develop a whole new body of physical law called quantum mechanics, which is so completely counterintuitive, which describes the world in terms of qualities that we don't ever see with the naked eye, but nevertheless, we can use the math to make predictions, and the predictions are borne out by experiment. And that progression only took, say, a couple hundred years. And that's where we've gotten. So it's kind of spectacular that, we beings who are just coming of age here in the Milky Way galaxy can sit down with a piece of paper and a calculation, a pencil, and we can figure out magnetic properties of particles like electrons to 10 decimal places. That's shocking. It's stunning. And it's something that I think all of us should be very proud of, that our species has been able to accomplish that.
In our vast universe, we've always been able to categorize the large and the small. From massive galaxies that stretch across the cosmos to the tiniest atoms that form the building blocks of matter, our understanding has grown over centuries. But there's a realm that doesn't quite fit, the world of quantum mechanics. Here, particles don't just sit in one place, they can be seemingly everywhere at once. Observing these particles can actually change their state. Time and space don't operate in the straightforward ways we're accustomed to. This realm is puzzling and fascinating. But why does quantum mechanics diverge so much from our everyday experiences? Why is it so profoundly counterintuitive?
You don't have, and neither do I, a quantum intuition about the wave functions and the probabilities that govern how a particle like an electron behaves. And that's simply because we were unfortunately or fortunately born as big creatures relative to the scales of quantum mechanics. And because of that, our intuition was never under any evolutionary pressure to understand how electrons behave. In fact, I like to say those of our forebears wandering around the African savanna who started to think about electrons and quantum mechanics, they got eaten. They're the ones whose genes didn't propagate onward. And therefore, those of us who are the beneficiaries of the survival of our ancestors, we're good at understanding Newtonian physics, but we're not good at understanding anything else about the deep reality of the world.
In all our explorations of the universe, quantum mechanics remains a puzzle. It leads us to ask, will we someday truly get it? Can we ever feel it deep down, as we do other natural concepts? Or will it always feel just out of reach?
We might be able to experience these distinct realms in such a powerful way that our innate intuition may begin to shift, to change, so that we grasp the quantum realm the way we grasp Newtonian physics. I can at least imagine that as a possibility. What it would take to actually get there, and whether our species will ever last long enough to actually have that kind of an impact on our intuition, I don't know. But it's all about experience and survival. We have been programmed by evolution not to understand the true nature of the world. We've been programmed by evolution to survive. And those are two radically different propositions, because you don't need to know the true nature of reality to survive. It's a distinct attribute, and one that is not necessarily one that has any survival value. To understand black holes, or the Big Bang, or general relativity, or quantum mechanics, or entropy, or thermodynamics, these qualities we develop as we go forward and try to understand the world, go beyond mere survival and figure out things that excite us. But it's not something which obviously has any survival value.
Let's dive into one of the most intriguing aspects of quantum mechanics, quantum entanglement. Imagine two particles that have interacted with each other. Even if you separate them by vast distances, a change to one particle will instantly affect the other, no matter how far apart they are. It's as if they're still talking to each other, sharing a secret connection. Einstein famously called it spooky action at a distance because it seemed to challenge our understanding of the universe. There's no signal passing between them. They just seem to know each other's state. This entanglement has been observed and tested in labs, proving it's not just a quirky theory. It's a real feature of our universe, raising questions about the very nature of space, time, and connection.
Now look, there's quantum entanglement, which is a strange property of the quantum world in which distant objects can behave as if they are one, and in some sense respond instantaneously to an influence in one location at a distant location, no matter how far apart they are. But that isn't really observing. That's more realizing correlations between physical properties at widely separated locations. But I'm not aware of a means of leveraging that to actually observe what's happening in some distant location, even if you do have quantum entangled particles.
Another marvel in the quantum realm is the concept of superposition. In our everyday lives, things either are or they aren't. A switch is either on or off. But in the quantum world, things can be both at the same time. A particle can exist in multiple states simultaneously until it's observed. Once observed, it chooses a state. This isn't just theoretical, it's been proven in experiments like the double-slit test. It challenges our classical views of reality. If something can be in two states at once, what does that say about the nature of reality itself? Are our perceptions truly limiting what's possible?
When you peel things back and you understand how it is that things have color and you have electrons dancing from one orbital to another, emitting photons at very particular wavelengths that are described by these beautiful equations of quantum electrodynamics, part of which that Feynman developed, it gives you a greater sense of awe when the curtain is pulled back. I mean, think about the collection of quantum events stretching back from the Big Bang until today that had to turn out exactly as they did for you and for me to actually exist. Each one of these quantum events, and there are nearly infinitely many of them, could have turned out that way instead of this, yielding a universe in which neither you nor I nor anybody else would be here. And yet against those astounding odds, we're here. That is cause for celebration.
In the perplexing world of quantum mechanics, there are mysteries that continue to baffle the brightest minds. The measurement problem questions why particles settle on a state only when observed. Then there's quantum tunneling, where particles seemingly pass through barriers that in classical physics would be impenetrable. We also grapple with the nature of quantum gravity, trying to reconcile the rules of the quantum world with the vastness of the cosmos.
You know, that and the deep interior of a black hole, I think, are the biggest mysteries that we hope the melding of quantum mechanics and gravity will reveal, will illuminate. And, you know, what question could be more captivating than why is there something rather than nothing, right? Why is there a universe at all? And will the theories that we're developing take us to an answer to that? I don't know. Even if we truly knew what the Big Bang is, and that's a big question in its own right, one would still be left with the question, well, okay, so you've explained the process by which a tiny nugget of a universe, a tiny nugget of space-time can undergo some kind of growth to yield the world around us. But presumably in that explanation, you're going to involve mathematics and some ingredients like quantum fields or matter or energy or something. Where did that stuff come from? You know, can we get to that level of explanation? I don't know, but it is remarkable that if you ask what happened a millionth of a second after the Big Bang, it's not really that controversial, right? Even though there's a lot of argument in the field, and it's very heated right now, I should say, regarding what is the right theory of the Big Bang? What is the right theory of early universe cosmology, where I mean early, much earlier than a millionth of a second? A lot of dissent, a lot of heated arguments about that. But you go like a millionth of a second after that, and we're on pretty firm ground. Isn't that amazing?